Okay, so like I said, this is the July session of the Databricks user group. As always, we sort of focus on trying to use all these Azure Data Platform tools to accelerate insights for your company and use that to improve the performance of your business. And so we at MLFLOW tend to focus on doing that with Databricks and Microsoft, our two major partners. So huge thanks to the Databricks blog and event teams for making all of this information available. I was able to attend a ton of sessions during the week of the conference, but this deck would not have been possible to create just based off of my notes. And you'll see throughout, there's a lot of primary sources coming from the developers and the marketing team that work with Databricks. So really you're getting this information straight from the source. And then, we're sort of, my role I see is sort of collating and assimilating what information is valuable and relevant to different skill areas. So thanks again to them. So I want to start with maybe the biggest topic coming out of the conference for me, which was Spark 3.0. So it actually came out the week before the conference was the final release on GitHub. But other than some documentation and some release notes, it's really hard to fully dig into this. So hopefully between everything that came out of the conference and then this presentation, you'll sort of understand how big of a release this is and the different things that it's improved that are going to make some of your workflows better versus just 2.0. If you are using Databricks already, in Databricks Runtime 7.0, you will be able to use Spark 3.0. There's sort of a coinciding release. So that would be how the upgrade works. And if you have any questions or concerns about going from Spark 2.0 up to 3.0, that's something we sort of can specialize in helping you with. So feel free to reach out to me. So let's start with the biggest new features in Spark 3. So the biggest one you're going to see is speed up in Spark SQL. And so if you look over on the right at the JIRA tickets that have been closed, sort of the breakdown, you'll see that almost half of the result tickets for this release are focused on Spark SQL, followed by the Spark Core. That has led to a 2x improvement over Spark 2.4. So this, you're going to see throughout them refer to this TPC DS benchmark. I've included a hyperlink here. It's a benchmark tool that's used to analyze decision support systems like Databricks. And so it's sort of a standard industry benchmark. And so we'll use those metrics throughout. So other than the resolved tickets, this performance improvement came from adaptive query execution, dynamic partition pruning, and a couple other optimizations. We're going to be digging into those in depth over the next few slides after this. And then ANSI SQL compliance, this is something that I would encourage you to look into yourself. Essentially, it's just a larger overlap between the ANSI SQL standard and Spark SQL in terms of what commands are standardized. I think one of the bigger ones is better reserved keyword support, some other things like that. And then significant improvements in the Pandas APIs. We'll be looking at those as well. The biggest thing here for me is the Python type hints. I don't use as much KOALAS since I kind of came to PYSPARK before KOALAS was really popularized. So I'm excited to kind of see, go back and see how I could potentially start using that more in the Pandas UDFs. But to me, Python type hinting is one of the biggest improvements in the Python 3.x stack that's been coming out. And I know in all my Python 3.8 code, I've been trying to use it as much as possible. So excited to see that come over to Databricks, and I think it's going to make my code more readable and cleaner. Also, better Python error handling and simplifying of PySpark exceptions. I was trying to find a screenshot for this. I couldn't find the exact deck from the conference where they were showing this off. But essentially, if you're used to your standard error messages for PySpark and Databricks, a lot of them are stack traces from the Java virtual machine. And so even like the example they gave at the conference was even something as simple as like a divide by zero error, which, you know, in normal Python, you would have a value error. It would very clearly tell you what's going on and you'd be able to isolate the problem and fix it. It's buried, you know, 20 plus lines deep in the Java stack trace before you actually get to your Python code. So they've done a better job of representing Python errors natively and showing PySpark exceptions in more meaningful ways to the user so that you can better fix your code. There's also a new UI for structured streaming that we'll look into. There are some 40x speedups for R UDFs. I don't use a ton of R, but I think this is one of those things that could, you know, potentially bring me back for certain applications. And then overall, just a bunch of JIRA tickets have been resolved, as you can see over here. Did I hear a question? Okay. So let's talk about the Spark engine. So you can see down here sort of the key to the story, which is this huge performance speed up over 2.4. So in this case, lower hours is better. It's still wild to think about the fact that we can process 30 terabytes of data in 7 hours, and seeing a 50% speed up release over release is huge as well. So what the Spark team did is, you know, and it shouldn't be surprising, but they use the data that they're able to get from the Databricks managed environment, where they can see what users are doing within their managed Spark environment. So they saw that 90% of Spark API calls are using the data frame, data set, or Spark SQL APIs, which I know is pretty consistent with my workload too. And so when they went to focus on improvements for Spark 3.0, that kind of tells you where you can focus, like what target area is going to give the biggest benefit to your end users. And so since a majority of even Python and Scala developers are pushing a majority of their work through the Spark SQL engine, then that makes it so that the 46% of patches in that JIRA graph that we saw for Spark SQL improve performance for all of that code. It's not just for things written using native Spark SQL. It covers anything in Python, Scala, or R that gets pushed down into the SQL engine runtime for, say, query optimization, et cetera. And so that leads to this 2x improvement in this pretty broad set of cases. So let's dig into those 4 features that, that really push this 2x improvement. So the biggest one is adaptive query execution. So this is not unique to Spark. This is actually something that's been a topic of research in the data engineering space for decades now. And it's one of those like holy grails, and it'll never be fully perfected. But the fact that some of this new research and these 2 new techniques are being integrated into what's already a really robust and performant SQL engine is pretty huge. And you can see on the right just the consistent speed ups. So on the top, it's showing sort of some worst case scenarios. And then on the bottom, you can see that for a pretty robust case, you're going to see kind of ridiculous speed ups. And so how does this work? Well, so since data, sorry, by data I mean storage. Since storage and compute are separate in Spark, which is one of its main paradigms, that can make it so that being adaptive at runtime is really critical. So a lot of systems where data sits at rest as part of the compute can do a better job analyzing that data statically during compilation, right? But since this is adaptive at runtime, a lot of these things focus on how to be adaptive to data that isn't as predictable as it could be. So the first one is dynamically coalescing shuffle partitions. So what this does is it lets the user set basically a wide net of partitions at the beginning of a query as sort of a hint. And then if the query planner basically sees that at some stage during execution, that guess was too big, it will dynamically coalesce the small partitions into larger ones. So for instance, if you said, I want to have 100 partitions, but each of those chunks is, 20 megabytes, and you have an optimal chunk size of 100 megabytes, it's going to dynamically drop that down to 20 partitions instead, and basically increase each partition size by 5 to target that more optimal size. And so this basically makes it easy for the user because you're not manually calculating partition sizes or doing a bunch of trial and error. You can say, this is my max, and then sort of set that as the threshold for the entire query. Now, this is a good time to point out when during the execution plan or the job, this is going to intervene. So it would be substantial overhead if during your job it was constantly polling to see, are there any things that we can coalesce? Are there any other runtime optimizations that we can do? And so really this only runs between query stages. And I had a graphic for this. I think it's in the appendix, but essentially when you get between different stages of a query is the only time that this is going to intervene. So there's no overhead to having this turned on. Then dynamically switching join strategies. So if you have inaccurate statistics about some tables, or the statistics are missing, maybe there's a size misestimation, the adaptive optimization of join strategies can automatically convert between a sort merge join to a broadcast hash join. Now, the broadcast hash join is our fastest possible join. And so if you thought that you needed sort merge, but the compiler figures out that you can use broadcast hash instead, that can not only simplify tuning because the user didn't have to intervene, but it's going to improve performance radically. So that is the dynamic switching of join strategies. And then dynamically optimizing skew joins is essentially making it so that if there's one side, typically like the right-hand side of a join, that's extremely imbalanced, that is going to downgrade performance because it limits the ability to use concurrency. So what the dynamically optimized skew joins does is essentially splits the skew partition into a bunch of smaller chunks that then can work with duplicates of the smaller partition, so that we can bring parallelism back in, and that lets you achieve better performance. So again, if you kind of picture this, like if you have this big table that's say 3 times bigger than the smaller table, if you split that into 3 chunks, then now you can do 3 lanes of work instead of just 1. So these are all part of the adaptive query execution framework. Any questions about this so far?
Hey, Spencer, yeah, I have some questions.
Yeah.
So what I'm hearing you say is that the AQE is the parent structure under which these 3 specific implementations fall. So then how is it on the right-hand side that one component of the architecture made a better difference in performance than the whole architecture?
Well, so these are just showing different use cases. So the x-axis isn't the same. So there's about 200 queries, and this is confusing to me too, but there's about 200 queries in this TPC-DS benchmark. And so they're comparing like query 77 up here versus query 25 up here.
So how did they choose that was you're leading it right into the next question. How do they choose those? How do we know that, I mean, it looks like this might be like they're cherry-picked results.
That's exactly right, Kevin, and very intuitive. And so I've included hyperlinks directly to the Databricks blog in this slide deck so that you can see the full data sets that they've made available. Like they make their benchmark set available. This is just coming straight from the queries that they wanted to extract. Yeah, so I think what they're showing is that so it's kind of two different messages. Up here, even in queries that are really hard to optimize, like they're not suited for AQE, it still is able to squeeze out a little bit of performance just through sheer will. Okay. But then there are some cases that are particularly suited to, for instance, the dynamic partition pruning, where it just completely shreds it. And so the dynamic partition pruning we're going to dig into in the next slide, and you'll kind of see why. But dynamic partition pruning is specifically optimal for star schemas, which I know we work with a lot. And so previously, like you'd see these high execution times because what it was essentially being forced to do is denormalize the data as part of your ETL process. Mm-hmm. And what dynamic partition pruning does is it takes advantage of your fact dimension structure to go ahead and basically only bring over the parts of a dimension that are relevant to this particular cut of your fact table. Yep. And so that's why you see this drastically improved performance.
Yeah, it's pretty dramatic.
Yeah, and so let's go ahead and jump over to that. So dynamic partition pruning basically makes it so that whenever the optimizer can't identify at parsing time what partitions can be eliminated, again, like in a star schema where it's split across multiple tables, like it could reference, multiple factor dimension tables, then we want to try and prune the partitions that the join is reading from a fact table by looking at partitions partitions coming from the filtering of the dimension tables. And so if you think about how Spark does its jobs, you start with a query written in a particular API. It creates a logical plan or rule-based transformations. Then it does a physical plan based off the statistics that's collected on your table, and then it finally pushes out to these RDD batches, right? And those are like your tasks. So if we look at a conventional way that this would be joined, like we have this huge fact table, and then we have this whole dimension table for date. Well, when we filter it, it's going to have to do a scan on both tables and then do a join, right? So the filtering isn't really being used as much. So what we'd want to do, if possible, is join the sales and date table, or the fact and the dimension, join that, do the filter on the larger denormalized table, and then do a scan there. So that's how it's previously been done, like on these left-hand queries with the dynamic partition pruning off. Whereas a quick example of what the dynamic pruning can do is go ahead and filter on this dimension table, see which partitions are relevant, bring that over to the fact table, and only scan the partitions that are relevant to the dimension table within your fact table, and then join on that. So you're doing a much narrower join. So those types of reusing of dimension table partitions allows for more hash joins, and that's why you see those significant improvements across a majority of these queries. And that's something I'd be happy to dig in more into during the Q&A. I have some other resources available that just didn't fit into this sort of tight summary deck. Okay, so let's talk quickly about the ANSI SQL compliance. So one of the big switches was to the proleptic Gregorian calendar. It also enables users to forbid reserved keywords within ANSI SQL as their identifiers. I sort of referred to that earlier. And so what this would look like is your Databricks administrator could essentially enforce at a workspace level for users to not be able to reuse those identifiers. And that would make it so that when you're, sharing queries across environments, like say you're taking something from Databricks and then you're going to reuse it in a SQL environment or vice versa, then you're going to run into less bugs going between the two environments. I know that's something I've had to manage in the past. There's also better runtime overflow checking for numeric operations, some compile time enforcement for data inserts, and some other things to improve data quality. Another big one is with join hints. So previously, the query optimizer has been able to fall back to shuffle hash and shuffle replicate nested loop join, but you haven't been able to specify it as a hint. So what you can do in this case is subtly speed up queries in cases where you know that it's not going to be able to do a broadcast or a merge, and sort of have it skip all the way down to either the shuffle hash or the shuffle replicate nested loop. So then, sorry, I need to go forward. So then looking at the Python APIs. So this focuses mostly on KOALAS, but there are some features for PYSPARK. So a big takeaway in this graph on the right, you can see that Python is becoming far and away the most popular language on Databricks. This has motivated a lot of the features that were in Spark 3. So a majority of people using Pandas APIs for data structures and data analysis and Python more broadly on single node processes makes it so that KOALAS is becoming more and more relevant. So KOALAS, for anyone who's not familiar, is an implementation of the Pandas API within Apache Spark. And so they've achieved this year 80% code coverage for the APIs between KOALAS and Pandas. That means that teams that have already been writing substantial code bases in Pandas are more likely to be able to bring that over with no refactoring to run natively on PySpark and take advantage of this massively distributed managed environment. So a part of that is making it so that different things like having, plotting support or support for UDFs are now natively integrated. And so by leaning into an existing popular language and a popular workflow for that language, it makes it more likely that users are going to be able to migrate over to Databricks, and it's sort of going to make that unified data science and data engineering workspace more of a reality. So some of the specifics here. So the Pandas APIs with type hints. So originally, when Pandas UDFs were introduced, took a ton of boilerplate. So the existing interface is pretty gross. It looks a lot more like Scala code than Python code, and it makes it even more difficult when you start to introduce Python types into the mix. So in this new release, the Pandas UDF interface leverages Pythonic type hints instead of having to use the more Scala style. And so that makes it so that Pandas UDF types are more easy to use. So anyone who's written functions in Pandas would be able to bring them over into PySpark as KOALAS UDFs, makes for more Pythonic and self-descriptive code. Similarly, there's two new Pandas UDF types. So the iterator of a series to iterator of a series, and an iterator of a multiple series to an iterator of a series. So that makes it so that you can do better data prefetching and initialization. That also allows for two new Pandas specific functions, the map and the co-grouped map. So I would encourage you to dig into that blog post if you're a big Pandas user. But essentially, these are two big functional style APIs that are pretty heavily used in Pandas data frames that are now natively supported in KOALAS. And finally, we've already kind of talked about this, with the better error handling, it makes it so that errors are more friendly to Python users. They're not JVM stack traces, makes them more Pythonic. Again, just enhancing the developer experience for a big core of their user base. And then finally, Project Hydrogen is Databricks hardware accelerated runtime. So it's an initiative focused on using GPU processes. So you can see some of the new configurations that are available in that hyperlink. I haven't gotten a chance to use this very much, but essentially it's making it so that Project Hydrogen APIs are more accessible through the existing RDD APIs. So it's more easy to leverage these new types of accelerators. So I could see this being huge for specifically like deep learning workflows. There's also a new UI for structured streaming. I've used the new UI or the existing UI quite a bit, and it's perfectly fine, but having a dedicated tab that manages this, similarly to like MLFLOW or some of the other built-in workspace tabs, is huge. So you can see over here on the right what that looks like. It just makes it so that you can keep track of those structured streams as they go. So if you have streaming jobs that are continuously running or run during certain periods of time, you can better aggregate information about those streaming queries and get better statistical information about those queries. And that'll be good for everybody. Similarly, having observable metrics that make it so that you can continuously monitor changes to data quality is a big part of data pipelines. That's a big part of our Databricks catalyst as well. And so this 3.0 release adds monitoring for both batch and streaming applications within those pipelines. So if you define an arbitrary aggregate function on top of a query for a data frame, then as soon as the data frame reaches a certain completion point, like whether it's the batch query finishes or the streaming reaches a certain epoch, then a named event is emitted out that contains those metrics. So that's going to allow for a lot better custom monitoring and more boutique enterprise solutions on top of complex data pipelines. There's also a new catalog plugin. So the existing data source API makes it so that you can't really manipulate the metadata of external data sources very well. What V2 lets you do with the new plugin API is for external data sources that implement both the plugin API and the data source V2 API, you can both manipulate the data and metadata of external tables via a multi-part identifier. And that has to take place after the corresponding external catalog is registered. But that could provide some pretty great use cases for the existing connectors that they've provided. There's some other high-level updates. I think we've covered most of these, but support for like Hadoop 3 and some of the other Hive metastores, Java 11, just some standard infrastructure and house cleaning stuff. But overall, a pretty huge release, definitely worthy of the 3.0 name and the 10th anniversary of the Spark project. Before we move on to the next generation data science workspace, I know that was kind of a huge info dump. Any other questions before we move on? Okay, great. So the next generation data science workspace is probably the feature that I'm most excited about. So the goal of this is to lean into the overall goal of Databricks, which is to navigate certain trade-offs in using a cloud-based environment for data science work and for collaboration with teams to try and make an open and unified experience that is modern and suits current data workflows. So they're focusing on having an open and collaborative notebook environment on a secure and scalable platform, a best-of-breed developer environment for GIT-based collaboration and reproducibility, and finally, low-friction CI/CD pipelines from experimentation to production deployments. So let's talk about how some of those features fit into the overall project here. So GIT-based Databricks projects. So once this is released, and I have requested the private preview, I don't have access yet. My understanding is that it's only on AWS so far. You're going to have a new projects tab on the left. When you click that, you'll be able to clone down a project from a Git repo. That could be Azure DevOps, that could be GitHub, that could be any other Microsoft Git provider. Tongue in cheek, you could really use any Git provider, even a locally hosted one, but that's what I prefer to use. When you clone that in, you're going to get a project created. So previously, if anyone's familiar with the existing Databricks Git integration, you had to manually link file by file. You couldn't even do it at the folder level. So this is going to truly make it a native experience. I'm sure Nick or some of the other software developers in the room are kind of scoffing at the fact that we didn't have this up to this point. But seriously, it's going to make it more like VS Code or Visual Studio, where it's directly connected and what you see is what you get versus your Git environment and what's local. So moves more towards CI/CD being truly native. So if you look at the workflow they envision, on Databricks, you can do your development and experimentation. You can version it on your Git CI/CD system, do your code review, do your testing, and then push it back into Databricks to run in production. So really, it's this closed loop like any other CI/CD or version control system should be, and now it's finally in Databricks. And so I'm excited to be able to use that, and I think that out of all these features, that's the one that I'm going to most immediately start applying to all of my projects. So this also facilitates project-based environment scoping through CONDAs. So I know that I've actually worked with some team members on this call on CONDAs for Python and setting up environments for different projects, and it hasn't gotten any better in the last couple of years, honestly. CONDAs and VM and a lot of these environment functions that are required for data science projects in Python are still just as miserable as they were when they started. What this is going to let you do is automatically configure environments through CONDAs as part of Databricks. So no longer, if you pass a project on to another team member, are they going to have to go through the process of library injection or making sure that their dependencies are in order. I know this is also a growing concern with Azure SDKs because, you know, like just for cognitive services, for instance, there's 5 different SDKs that are all named similar things. Some might only have like, you know, a dash difference. Like it could be Azure Dash ML is the new one and Azure ML is the old one. And it can be impossible to collaborate like that. So having this as part of your repository, this requirements.txt, and making it so that when you clone down the project, everyone gets the same environment that has all the correct libraries, all the correct dependencies is huge. And since this is Databricks, they went one step further. So once you get this working with like, say, your laptop, it feels amazing. Well, what Databricks does is makes it so that once the environment is created in your project, all workers, even on auto-scaling clusters, all consistently have the same environment enabled. So no longer do you have to make sure that, for instance, like if you're doing MLP, you cache a dictionary on every single worker within your cluster. It's all managed by Databricks. Similarly, there's now support for Jupyter notebooks. So again, if you're working on cross-platform teams that maybe didn't start with Databricks or migrating, you're probably going to have a lot of IPython or Jupyter notebooks floating around. Well, what Databricks lets you do now, as you can see in this picture, is natively open Jupyter notebooks as if they were written in Databricks, which is huge. But you can also natively open the JUPYTER GUI within Databricks. So if you have those keyboard commands down spot, or you have some other reason for wanting to use JUPYTER, you can now do that natively. So it's, again, one of those things that's going to make it so that more teams can move to Databricks easier with their existing code bases. So thrilled to see that. Now let's talk about MLFLOW. And actually, I guess before I move on, any questions about the modern data science workspace on Databricks? Okay, great. So a big thing that, again, is sort of house cleaning, but I wanted to make sure and mention it, is MLFLOW is now a part of the Linux Foundation. So Databricks actually donated it as an open source project to the Linux Foundation project. And so that is encouraging because essentially, even if Databricks were to tank, now you could be assured that all of your MLFLOW and ML libraries written on MLFLOW are going to continue to work as long as Linux works. So it's this vendor neutral, nonprofit way of having the project managed long term. And so it's not only going to add stability to MLFLOW, but also hopefully open it up to even more open source contributions in the future. Then this one is another thing that I'm super excited about. So MLFLOW now has model serving. So MLFLOW model serving is a turnkey solution for hosting ML models as REST endpoints that are updated automatically. So in the past, ML engineering has been tricky in its own right, but then when it comes to making it to production and serving ML models, it suddenly becomes more of a web development project. You know, people do it with Docker, Kubernetes, whatever, but you're managing different microservices. There's all sorts of different paradigms for making REST endpoints for these models. What having a turnkey solution does integrated with Databricks is let a data science team own an end-to-end life cycle for a real-time machine learning model. So you can go all the way from training to production, all without needing to contact IT or talk to a web developer or whatever. And so this makes it so that data scientists are able to do more experimentation, try out more models, do a high volume of predictions without latency being an issue, and that is only going to enhance and accelerate their development lifecycle. So if you need to do predictions at some sort of low latency, you've been using REST endpoints, and this allows you to just deploy your own to an endpoint that's always up, always ready to receive the prediction. You're not switching between your Databricks tab and your Azure portal tab. It just makes it, again, turnkey. And so if you're used to the MLFLOW Spark UDF, it's very similar. It allows you to deploy in either batch or streaming fashion. And then if you need to do it in real time, you can now just say, I want to do it using the MLFLOW model serving layer in the way that you previously would have specified some other host like Azure. It's now just built in. And this all integrates directly into the MLFLOW model registry. So a lot of these topics we talked about last month, like the MLFLOW model registry. And so if you remember that, it allows you to track versions of models and specifically route requests to them. So if you're hosting if you're doing model serving on Databricks and you're hosting within the MLFLOW model registry, you could say, I want this model to be deployed to this endpoint, or I'm ready to move this model up to production, and you're managing that all natively through the Databricks environment. So if you look at the way this works, we're consuming all these different libraries into a couple flavors of models. One might be our current production, one might be something that we're doing in development. And you can push it out to these different stages of your life cycle within your model registry. So you could have some that are in staging, different versions of those staging, and then maybe we're really happy with V2. Well, we can push it up through production, we can push the other ones into the archive, and then we can deploy that to our REST endpoint to be consumed by Power BI or maybe a Cosmos DB application, whatever it is. And it's exposing these models as REST endpoints all through Databricks. And so if you have different versions of a model, a machine learning manager could come in and promote them from different life cycles. So they could say, hey, I'm looking at these metrics for the model the team turned in last night. This one's ready to go to production. And so since it's stored in a hierarchical way, you could go to model name, and then production, and have that URI available. Similarly, if you want to do /staging, that's always going to be staging. And under the hood, the model serving manages whatever clusters are needed to execute the requests and ensure that everything's always up to date and healthy. So it again lets data scientists focus on data science, not on all these engineering and web application tasks. You can kind of see what this looks like. So once the model serving is enabled, a cluster launches, it hosts all active model versions associated with that particular model. So you can see like version 7, 8, and 9. And then the model is running in a CONDA environment that reflects the exact environment it was trained on. See how these pieces are all sort of coming together, the model registry, the new CONDA support, etc. And then once that's running, you can do all these tests within the UI. You could submit them yourself using any testing environment like Jenkins that uses REST APIs. And then if you want to integrate with the new model schema support, you can even have annotations within your model and example inputs to make it even easier to test out your served models. And then when you're ready, you can click on one, and I think they're going to show here at the end of the GIF promoting it to production. But regardless, you kind of see the idea there with this integrated call and response. And I'm sure, again, the app devs in the room are kind of surprised that we haven't had this already. But, you know, here we are. This is all very new and constantly evolving. So similarly, once you start with a proof of concept model, you can push it up through different stages of production via those URLs like we talked about. And you can see this little tag for production versus staging. And so if you're ready to promote something to production, you can transition it within the registry up from staging to production. And then that change is going to be reflected in the URL nearly instantaneously within a few seconds. And the prod URL will now point to the different version. And since everything's running on the same cluster for hosting, there's very marginal resources and time involved in spinning up a new version. You don't have to worry about some multi-minute iteration cycle or old versions being lost. So this is all sort of a maturation of these existing processes. Then finally, model monitoring is now more integrated. So since you're serving through Databricks, you can see logs for each model's consumption through both a new UI and an API. This makes it easy to omit and also see issues that are related to runtime errors, malformed data, whatever it might be. And since the events supplement the model's own logs, you can see when a model process crashed, was restarted, if a whole virtual machine was taken out. And so, you know, this sounds really basic, but having access to these types of logs and events makes it so that the development, iteration, and maintenance lifecycle for model servers is less time consuming, and you can focus on more critical tasks. So this is another private preview. I'll be talking more about some of these things as I get access and trying to give some demos. Another new feature is auto-logging. So this was actually introduced in Spark or in MLFLOW 1.8, and that was sort of the initial version of it. What auto-logging lets you do is essentially, if you're using, say, the Spark ML library, mlflow.spark, if you do .autolog as part of your model, instead of you having to specify which parameters to track, like you can see over here on the right, all these different metrics and parameters, it's going to do it automatically. And so what they're doing in 1.9 is just enhancing the coverage of which libraries are supported with autologging. So now it's fully integrated with Spark ML as well. If you're using Delta Lake, this is also great because it natively integrates with Delta Lake versioning. So if you wanted to go back and see some autologged metrics for a particular model, and you're wondering, wait, why is this performing so much better than it is today? You could literally time travel that table back to whichever version you're interested in auditing, and that lets you debug or reproduce results all natively. And that's, again, some integration between Delta and some of the new features of MLFLOW. Now, this is another feature I'm pretty excited about, model governance. So previously in MLFLOW, there was no sort of schema or governance enforced on ML models. So you could run into issues, especially in production, by basically trying to use some old schema for a model, or maybe versions are out of sync. But one of the biggest sources of production outages for ML is a schema mismatch when a new model is deployed. And so now that a schema is integrated with the model registry as part of the model metadata, MLFLOW allows you to compare model versions and schemas and alert at runtime if there's incompatibilities. And so that also, excuse me, requires tags. Facilitates tags. So for instance, if you're working with GDPR, you can have new tags saying that this model passed GDPR review. And so if you wanted to make sure that something is compliant before it's being deployed, you can have these tags integrated. And so if something hasn't been audited for GDPR, the model registry is going to prevent it from being served to production. So since it's integrated with the APIs, that could be included automatically as part of your CI/CD pipeline to test which models have which tags, add them, make it easy to check what's ready for deployment and what's not. And then finally, the serving environment. This is sort of what it looks like. We've talked about it quite a bit, but that sort of turnkey environment. Then finally, REDASH is now part of Databricks. So this is sort of a visualization layer. Think of it as Power BI, but more for ad hoc sort of data science workflows, like if you're trying to do exploratory data analysis. I had not heard of REDASH before this announcement, so I was not really expecting it. Haven't used the product before, but it looks pretty great. Essentially, what you're able to do is have a built-in query editor, have visualizations and dashboards, have collaborative sharing, schedule refreshes, schedule alerts, have a REST API that makes it so that you can programmatically manage the UI, and then a broad number of data sources are supported. So sort of similar to what we've seen in like Tableau and Power BI, but again, always happy to have this more integrated as a Databricks tool. I think that this is going to be great for monitoring other ad hoc workflows, exploratory data analysis, that kind of thing. And also having it natively included in your workspace makes for richer collaboration. So you can say, hey, I was looking at this new data, take a look, it seems like there's this type of skew, making it so that you can more easily collaborate with other members of your team. Then maybe the biggest announcement I saw was Delta Engine. So what Delta Engine does is ties together an Apache Spark compatible vectorized query engine with modern CPU architecture optimizations to the Spark 3.0 query optimizer, and adds caching capabilities, etc., all as part of the Databricks Runtime 7.0. And those features essentially accelerate queries on top of Data Lake specifically. So it makes it easier to adopt a lakehouse style architecture at scale in a performant way. So one of the things that's happened over the last 10 years with hardware is clock speeds on CPUs have plateaued. You know, I have a CPU in my desktop that's about, I think, 7 or 8 years old, and it's still hard to find a CPU on the market that actually has a higher clock speed. So what's really changed is multi-threading and parallelization. So one of the best ways that we can speed up data processing beyond raw compute power, which isn't really available, is having better parallel processing algorithms. So data processing engines have to be specifically architected if they want to be able to take advantage of parallelism. So data teams being given less and less time to properly model data as the pace of business increases leads to poorer models, makes it so that business agility is emphasized instead of query performance. So how can we maximize both agility and performance? Well, what Delta Engine does is accelerates the performance of Delta Lake for SQL and data frame workloads in 3 ways: an improved query optimizer, a better native execution engine called Photon, and enhanced caching between the execution layer and cloud object storage. So fully compatible with all Spark APIs, built natively for Spark 3.0 with an emphasis on these 3 accelerations and improvements. So the query optimizer extends functionality in Spark 3.0. We've already looked at the cost-based optimizer, AQE, dynamic runtime filtering, and other advanced statistics to deliver up to 18x performance in star schema workloads specifically. Similarly, the Delta Engine caching layer automatically chooses input data that gets cached for the user and makes it so that it's transcoded into a more CPU efficient format that takes advantage of SSDs specifically and also modern CPU architecture. This delivers up to 5x faster scan performance for virtually all workloads on Spark 3.0. This talk specifically on Delta Engine in the keynote at the conference was one of the coolest things I saw. They were actually doing breaking down some C++ code as part of their presentation, and it was really neat to see. It really is quite like clearly an engineering conference instead of a marketing conference. And then finally, the native execution engine. So they announced this is called Photon, and so it's an engine within an API or runtime, right? But it's an engine for Databricks specifically that's been built to maximize performance of modern cloud hardware. So it elevates and improves performance on all workload types while maintaining compatibility with existing Spark APIs. So it does that through data level and instruction level parallelism, and a couple optimizations they made for modern workloads that are not just benchmark focused. They really looked at what users are doing and focused on that. Faster string processing and faster regex. So if you have a bunch of hashable keys, your performance is already pretty great. But in reality, a lot of us are matching strings. A lot of us are doing pattern matching with regex. And so by natively focusing on how to store that information in an enhanced CPU native way is huge. And so similar to Azure Synapse, this is focusing on being a cloud native solution for the compute aspect of a data lakehouse. And so if we look at, you might remember this graphic from our first session, and we're going to dig into this actually in the August session as the data lakehouse. This big data lake that combines compute and storage on Delta Lake and pulls in your structured, semi-structured, and unstructured data along with a transaction layer. What the Delta Engine does is sits in between that and your consumption use cases and essentially speeds it all up. It's just a high performance query engine. So the architecture was already great, and this is bringing cloud scale performance to it to make it more efficient and more usable for all those applications. So it really is one of those things that, like, I certainly was wondering what the response to Synapse was going to be, but now that that piece is in place, the overall architecture makes a lot more sense than it did before. So really excited to see how Delta Engine works in production. That is all the things I wanted to cover today. We've got about 25 minutes left over for questions, so let's dig into some of the nitty-gritty here.
Hey Spencer, just a weird question for you. You're probably not going to be able to answer it, but something I've been hearing about lately is that as models become more and more complex, you mentioned the limitations of raw processor capacity. Some things that I've heard of is that as models become more complex, it seems like we're finding opportunities to use graphic processing for like.
Yeah, absolutely. Yeah, CUDA, and that's what Project Hydrogen is. Yeah.
Okay. All right. Cool.
Yeah, so let me actually let me go back to that slide real quick to sort of show what Kevin's talking about. So essentially, on a GPU, you might have cores that are, you know, about 1 gigahertz, or approximately a third of the raw compute speed as a CPU, right? But the difference is, like on modern ML focused GPUs, you might have upwards of 2,000 cores all running at that clock speed. And so certain tasks, like for instance, watching a movie or you know, compute intensive things, they can't scale very well to that. One of the things that can is deep learning. There's our slide. And so this accelerator aware scheduling allows you to specifically fall back to GPU acceleration for specific workloads like deep learning, where it's massively parallelizable, and you don't necessarily need a high clock speed to take advantage of that. You just need a ton of tiny processors. And so if you dig into these links, you can actually see, and let me go ahead and pull it up. There's some new configurations available that let you take advantage of this new hardware that they're offering. And basically, it's just a part of your Hadoop or Hive configuration is to say, I want to use GPU scheduling for this particular use case. Any other questions? Anyone want to share parts of this release that they're particularly excited about, or how they envision themselves using it on some of their projects? Give some other folks some ideas. Well, if not, I'm more than happy to give everyone some time back. But you know, thanks for tuning in, and feel free to reach out to me privately if there's any other questions you have, or topics you'd like to see covered in future sessions. But I'm certainly thrilled about this release, and I'll be talking more about all of these topics throughout the rest of the year, especially as I get access to these private previews.